So when I see this quote, since I'm an engineer, unfortunately, I see a graph. I see a 2D graph here. And on the x-axis, I see the filling of the vessel axis. And on the y-axis, I see my kindling of the flame axis. And Socrates, I don't think, had this in mind when he was talking. So here I am as a faculty member sitting down here at the bottom. It's Monday morning. I haven't had my coffee yet. And I'm trying to figure out what I'm going to lecture about this week. Now, the traditional lecture from maybe a generation ago would have come straight across this axis, and we would have designed this really, really intense lecture and covered everything in 50 minutes and made sure we got through it all. And the student evaluations would have come back at the end of the semester, and they would have said, you know, Professor X just did all this random disconnected facts that he threw at me all semester long, and yeah, I passed the exams, but I have no idea how they go together or what they mean or why I had to learn that second-order differential equation in the first place. So it was just all this random stuff, no context. So the professor comes back, and he's a little bit frustrated. So he designs what he's going to do the next semester, and he says, you know, I heard this bozo named Kander talk about kindling the flame stuff, and you know, maybe I ought to design my lectures to really, really do that. So they go up this axis, and we've all met the faculty members who do just this, too. And, you know, these are the ones who stand up in front of you and tell you war stories about when they were in industry for like 50 minutes. And the students love them, right? This is great. And, you know, it's a really great, you know, entertaining day, and you hear all these interesting stories. Of course, at the end of the semester, you haven't actually learned anything, but the stories were cool, you know. So that's really not a good solution either. So how do you get in there to where you really want to be? And, of course, I think you see where I'm going. The trick is to get in that upper right corner. How do you get all the content you need in and still kindle the flame so that people are interested? And I propose that the way you do this is really by getting away from the lecture mode and focusing on really deeply integrated projects and case studies, problem-based learning. The best way to learn is to get in the lab, get in the studio, get outside, get a project, go build a Baja car, do whatever, but it's to get in there and do something in a project-based context. But it's got to be really deeply integrated with everything else you're doing. So as much as I respect and admire Socrates in his quote, I have a small editorial improvement that I will humbly suggest to Socrates, and that is maybe it's not a not, maybe it's an and. Maybe it's that education is the kindling of a flame and the filling of a vessel, because if you don't walk out with your disciplinary content, it doesn't matter. So it's easy to say, right? Now the big problem with this is that's a great thing to sit up here and talk about on a cool slide. It's how do you actually reduce that to practice and do it, because it's not that easy. It's great. We can all nod our heads and say, yeah, that's what we ought to be doing, right? It's the how that's the problem. So that brings me to my second really cool quote. In theory, there's no difference between theory and practice. In practice, there is. I love this quote. If you look this up on the internet, it's either attributed to Yogi Berra or to Albert Einstein. And I contend that any quote that could plausibly be attributed to both Albert Einstein and Yogi Berra at the same time by itself is a cool quote, just for that fact right alone. But actually, it's kind of a neat quote if you really look at it, because this is really the problem. This is it. This is the meat of everything that we've ever talked about in terms of how you teach in a university. It's really easy to come up with all these theories, but when you actually go to do it in a classroom, and you've got a budget, and you've got a certain amount of space, and a certain amount of equipment, and a certain number of students, how do you actually pull it off? So rather than spend a ton of time talking about lots and lots and lots of different curricular models, what I'm going to do is give you a simple case study, because I just said that that's a good way to teach, right? So I have to do it. So I'm going to pick one course. We're doing this across our entire curriculum, but I'll just show you one example of the kind of thing we're doing to try to mix up the way we teach these kind of subjects. So this is an Introduction to Engineering course. This is the course I mentioned that happens in the second semester freshman year. And it's your introductory survey course. It's 3 credits long, but it's 1 lecture, 2 lab hours, so it's actually 5 contact hours a week. We boot the lecture. We actually spend all 5 hours in the lab because there's no use having a lecture. And the way we design this course, it's basically built around a whole bunch of design problems and project-based challenges. And these range from 30-minute challenges. I'll walk in class sometime with an instant challenge, and I'll just have bags of junk. Like I'll have a bag that's got, pipe cleaners and and sticks and balloons and tape and stuff in them, and I'll just hand each group of 2 students a bag and say, okay, take everything that's in this bag, including the bag. You have 30 minutes to build a structure that can hold a golf ball as high off the table as possible. Go. You know, and then we come back 30 minutes later with the yardstick. I have a golf ball. We lay it on the structure. It has to stand there at least 10 seconds before it collapses. If it doesn't collapse, we measure it. You know, the winner's the highest structure. From things that small to a 8-week-long project in the course that's a really well-designed. They built solar towers last year to try to capture solar energy and turn it into electricity. So what I'm going to do is show you a 2-week project as an example. This is a reverse engineering project. And you can imagine this as in any kind of introductory engineering or science course, actually, as a discovery project at the beginning of the course. So in this reverse engineering project, we start by giving every student team of 2 an electromechanical device. In this case, we used a hand mixer from Target, $7. Gave everybody a $7 mixer in every pair of students. And these design studios have toolboxes for each student group. So there's some pictures at the top of the students ripping apart one of these blenders or mixers. There's a lot of reverse engineering projects out there that people do at universities, but what I want to focus on here is the deep structure to what we're doing. So they take this thing apart. They have to disassemble it in a very controlled manner, and systematic is the key word. It's easy to rip it apart. It's hard to rip it apart in a systematic way. So you have to take it apart, desolder all the wires, take every single component apart, and the extra credit at the end of the 2 weeks is can you reassemble it and have it still work? So you don't want to just sort of destroy it. So you have to take it apart in a very careful way. Next thing you have to do is inventory every single part. So you weigh every part, you determine what it is, you determine what it's made of, and you form a Excel spreadsheet of an inventory of all 60 or 70 parts in this thing. That alone is an interesting lesson when you realize a $7 hand mixer has about 70 parts in it, individual pieces in it. Pretty complicated design for a $7 item. After you get that inventory, you then have to use a concept mapping software package, and you draw a functional map of how do all these parts interact with one another functionally to produce the outcome, which is a spinning set of beaters at the end of the mixer. So how do these parts interact with one another functionally to form a functional relationship map of how the thing works? And that's pretty darn complicated because there's parts that serve 4 or 5 functions that loop back and do 2 or 3 things inside this little hand mixer. Then we use an interesting eco-audit. This is the CES software. It's a software package that actually Rick knows about this. He's used it. There's a software package we use that allows you to do eco-audits. And what it does is takes all this part inventory information, plus it takes, and we know what size motor is on this thing. We know how long it's going to last in its life. We make an estimate. So you know how much power it's going to use. And you look at what your power grid is in your area. You can figure out how much energy that's going to be and what it's coming from. We also look at where this thing was made. In this case, it's made in China. So we can look at the transportation costs of this thing coming from China to the United States to a distribution center, from the distribution center in a truck to a store before you buy it. And if you put all that information into the software, what it'll do is an eco-audit over the life cycle and tell you how much energy and how much CO2 emission is associated with the materials, the manufacturing, the use, the transportation, and the disposal, all the 5 stages of the life of this product. And it'll let you see where the energy use is and where the CO2 emissions are in the life cycle of this product. So now that you've done that analysis, you can now propose an improvement. What can I do to change this mixer to affect either the energy output or the CO2 emission, or make it a better product, or make it a cheaper product, or improve it in some way? And you propose that improvement, and then of course you have to go back and make estimates of changes to these things to show me how that improvement might impact. Of course, you don't have real data now because it's a proposed improvement, but you have to make good engineering estimates about how you're going to change some of these numbers and where the change is going to occur in the life cycle. Usually you find out that there's one dominant piece in the life cycle. So let's say, for example, in this, that the materials were the dominant piece. If you make a change over here to the energy of the motor, you might find out that's insignificant to the overall life cycle energy use of this product. for example. So you got to make an intelligent decision in proposing an improvement. And then finally, and this is the part that I think is the most important piece, is I stop the class, everybody has to pull out a sheet of paper, and real time write a page or two of reflection about what just happened. What did we just learn about this product and about the design process and about sustainability from doing this exercise? You know how much people love the fact when I have them rip out a sheet of paper and write for 20 minutes or 30 minutes? You know how much you enjoy that when you have to do that in class? So you write for a while, and then we as a group come back together and start talking about what happened. And what's really cool is this sort of natural 4 pillars start to pop up. And the conversation very rapidly turns to cost. And what do we mean by cost here? And remember, this thing costs $7 at Target. And all of a sudden, people start asking questions like, okay, does that $7 really capture all the cost associated with this product? Is that $7 counting for the emission releases associated with transporting this thing from China to the United States? Not really, not yet. Is that cost taking into account the fact that there's probably somebody working in substandard, maybe unsafe working conditions that's getting exposed to maybe some dangerous materials in the workplace in China? Is that in the $7? Probably not. Not yet. You know, so how do we take care of that? And do we take care of that? And there's usually somebody at this point that's really riled up in the audience, you know, one of the students that's really into the sustainability thing. And I say, okay, you know, you're really into this. You're going to design, you're going to start the super sustainable mixer company. And you're going to make sure that every penny of cost associated with the life cycle of that mixture is captured and goes to the consumer. So you're selling your mixers for $50. And they're on the shelf right next to his mixers. And he has the I don't give a damn mixer company who's still selling them for $7. And his company's out of business in about 8 nanoseconds, because if you walk up to the shelf, you're not going to buy this mixer if I can buy that mixer, right? So capturing every penny it costs and passing it on to the consumer, that's not a good solution. You can't have an impact. You know, not giving a damn and selling the $7 mixer, that's probably not a good solution. So what do? You know, it gets pretty hard now. It gets kind of, there's not a real nice, clear solution about what the right path forward as an engineer or scientist is when you're attracted to a problem like this. So it gets to be a really rich discussion, you know, $7 mixer, freshman class, second semester. For those of you who do education work in the room, you'll probably start to recognize that this systematic 6 steps walks you right through what's called Bloom's Taxonomy of Learning. For those in the audience who don't know what that is, there's a theory about how you learn that says you start at sort of lower level learning and you walk up through to higher level learning. At the lower end, you're doing things like just knowledge comprehension. Then you're applying tools and doing some analysis. And then you get to where you synthesize your ideas and do critical evaluation. And this is where you're starting to do critical thinking. And so in a 2-week time frame, you very purposefully walk students all the way through to where they're asking some deep questions about sustainability at the end of the experience. So what I've tried to do here is show you just one very simple example about how I think you ought to take this balanced approach. If we go to our friend Socrates here, you need to somehow balance this kindling of the flame and filling of the vessel if you're going to talk about things like sustainability in a curriculum. And, you know, I'm proposing this definition of sustainability that includes technical, financial, environmental, and societal. And I think you have to take all of them into account in any one problem you look at. But, you know, a nod to our friends Yogi and Albert, though, that it's not easy to do. And you have to have a way to do this that's practical. And my practical idea is that you focus on these really, really, really hands-on, deeply integrated, project-based experiences that force you to go through that whole sort of thinking range every time you do a project. And I've always been a strong advocate of the fact that you don't ask freshmen simpler questions than you ask seniors. You ask freshmen really complicated, ugly, dirty questions. You may not expect as sophisticated an answer yet when it's the first time you've seen that kind of problem. And by the time you're upperclassmen in a curriculum, you would hope that your answers are more deep and more sophisticated. But it's really a disservice to give you simpler problems at the beginning. You should see the ugly, dirty, full of real-life problems from day one and try to ask questions about the mixer and what it costs and what that means to society from day one. So that's kind of the approach that I'm talking about here. We do this, that was one example. We do this across every single course for 4 years. These are just a bunch of pictures of that's one of the bikes up there. The gentleman in the yellow shirt right here is the guy that has cerebral palsy and is riding one of the bikes. These are all bikes that were different models. These are some of the solar towers in the middle. We also have the students build devices to fling one of our mascot dolls to targets. All kind of interesting stuff. That's one of the golf towers over there. Instant challenges. So that's what we're doing. The biggest problem in doing this is faculty. Finding people who like this model, want to teach this way, have the skills to teach this way, a lot of professional development to get faculty trained. Let's face it, all of us that are faculty learned how to teach way back when everything was done in very traditional disciplines. So this idea of working on complex interdisciplinary problems in the classroom and problem-based learning is not something everybody was exposed to. So we're all relearning how to do this. So you got to go out and find a bunch of, it's a really motley crew of faculty. We just hired 2 new faculty, so we'll be up to 12 next year, that want to teach this way. But it's a really good way to get students heavily engaged in these sort of practical skills. Go back to the things industry is looking for. You want them versatile, you want them practical, and you want them to understand sustainability. And if you focus on the kind of problems I just showed you, you get to do all of those at the same time. Because in the process of taking that mixer apart, you learned a little bit about soldering and how wires come out and what circuit boards look like and about different materials and about a bunch of things that are practical pieces of information. So that's all I'm going to talk about. Let me stop there and open things up for a few questions or comments or discussions. Thank you very much for your attention.
Anyone have any questions for Dr. Kander?
Everybody understands everything. Yes, sir.
For ABET, on your advisory board, did you have to kind of pick and choose in order to meet the criteria of your industry board that supported?
Yeah.
Did you have to drop maybe some?
No, I'm an ABET evaluator. I'm a PEV. I'm a program evaluator for ABET. So I looked at it pretty critically. And as a general engineering degree, you have to meet the A through K requirements. You don't have any program-specific requirements because you're not a specific mechanical or electrical or whatever. So you just have AK. So if you look at just AK, not hard at all to justify that this curriculum hits all that. You still have to show that you have enough credits in the engineering sciences and stuff, but that's easy to do. We definitely keep that, stay above that threshold. That's a good, yeah, very good.
You presented a very diverse perspective of what sustainability is, and that is probably different from the traditional mindset that we consider when we think about sustainability. How should we take maybe traditional classes that we're in, or the mindset of the curriculum we're currently in that may be a little bit different from this, and think in that golden picture of sustainability?
It's interesting. With existing faculty, and I have a student that I just had do a senior thesis on this, and she came up with an interesting perspective. She's going to go to grad school. She wants to be a university professor someday. And she said that until her generation become faculty, there won't be a set of faculty everywhere that have been taught in an interdisciplinary way. So there's sort of a patchwork between now and then. And what I think works the best is a lot of team-taught courses. So and I mean team in the broadest sense. So if you have a course, say, in design or in mechatronics, right? Bring in a social scientist who can do some things in the classroom with the students in the context of the projects you're doing that talk about, what are the social impacts of robots in the workforce? What does it mean to put robotic manufacturing in place when you're going to displace factory floor jobs? And how does that work into the sort of life cycle, or electric cars? Get somebody to come in and talk about, okay, how do you recycle the precious metals in the batteries of the electric cars? If you're really going to talk about the life cycle of an electric vehicle being zero emission, it's not, right? The energy came from somewhere. So you got to get other people in the classroom other than the technical instructor to broaden the discussion at some point. You know, and it doesn't take long times. Like this was a 2-week project, so you know, teaching for 15 weeks, you have somebody come in for 2 weeks while you're doing a project.
As a follow-up to that, I guess from the student's perspective, you would tell them if they're in a traditional class to think more globally in terms of what content they're learning and how that would apply to a societal
Absolutely, yeah.
perspective on
Students in the room, how many of you, either on the web or in physical form, read a newspaper every day? Yeah, see, that's, you know, that you need to know what's going on. You know, like, you know, what's happening to the budget in the federal government right now, you know? And how's that going to impact your ability to do what you want to do 5 years from now? You know, how are the legislation on clean water and renewable energy going to affect what jobs you're going to have access to when you get out 5 years from now? You know, so you need to plug into some of those issues and ask some questions in class. If you're in a alternate energy class, it's perfectly appropriate for you to ask the faculty member about federal policy associated with wind energy, not just a technical question about wind energy. And if that faculty member doesn't know the answer, that's okay. But that means you guys can maybe go out and do a little research as a class and look some things up and come back to class and talk about what does it mean for jobs in green energy if the offshore wind doesn't happen in Virginia. You know, those are important.
Any other questions? All right, let's thank Kander again.
Sure. Thank you, guys.